Hello everybody and welcome. This is No Orientation Programming. I'm Joe, and today, I hope today is the day where we will finish, I don't know if we will finish the process file executing, but hopefully at least we see some progress today. The last days we extended the interface more and more, and I think now we have everything we need. So let's see, the state machine has changed a little bit. Oh yes, so we want to have a full communication with the process. And the possibility to route the inputs and output streams. I think I will just begin. So in the beginning we have the parent process, and the parent process is creating a file executing process. This file executing process gets a command. For example, we can set a lot of stuff for this output, for this command, like the environment. Oh, I have eaten so much. Oh, so bad. We can, yes, on default, if we start a process, the source is closed and the sink is set to discard the data coming from the child process. So we have to enable the sink if we want the output of the child process, if we want to receive stuff, if we want to receive data. Then we can add a sink, I don't know, sink, should we call it destination? I think sink is okay. To add a sink means that we want, for example, we can, if we enable the sink, then we are able to manually read the data from the child process. But if we add a sink, then the output is in automatic reading mode. Storing the data in some buffer or a string or another file, stuff like that. And for the sink, we have the special case that we have two sinks in general, the standard output and the standard error. On default, we set all the stuff as standard output stream. So that's okay. In this example, we just add a command and then we set the environment for this command. So how is this working? In the function environment set, we check if we have some command in the execution list. If we add a command, then we create a new file executing process, the same type of process we have here. So we have a second stage file executing process. This process is created but not started immediately. That's dangerous to have a memory leak. That's dangerous. That's important. Okay, yes. So we have to be careful. Because if we create the process and as soon as we start the process, then the process is in our child list, and the last time point in which the child file executing process is cleared is when we are repelled by our own parent. So, but as long as these processes are not started, they are just on the heap. That's just a heap allocation, and we have to be careful. Okay. We could do something else theoretically, but no. Whatever. We add another variable called internals started. Timeout, okay. False. Then we need a mutex. Mutex config, and then config done. Config done, config closed. So let's see. We need this for every function that can change something. Like these. If we change something, the configuration, and then we start the process, then we cannot change the structure again. We can only have read stuff. That's okay, but we cannot add a command during execution. So we have ms timeout set guard mx config. Let's see if we can compile this. What? Oh no, guard lock. Yes. Something like that. And if config closed, return this. So that's it, I think. That's bad, but we have to add this for every function. Source enable, source set, command add. This is not going to work. Ooh. Nah. Okay. I hope at some point that this send close. Oh no, command add. Whatever. I hope that this process has an end at some point. So this is the internal thing. Here we say this and then return that command and argument. On the other hand, Okay, let's see. We need only oh, int command, internal command add. This is strange because we should have 3. Ah, yes, we have 3. Okay. That's not cool. So that's it. Oh, I'm so full. Okay. Okay. Now we need to add this in the high level functions. Yes. Okay. Environment set if closed return. Sync enable if closed return. Sync add if closed return. And we have to use a mutex because the process may run in another thread. Does not make sense, but it's possible. So error redirect, and that's it. So this is changing the configuration, and we have to 900 lines is way too much, and it will be a lot of more. So this will be a quite complex process, but I think it's still a unit. So I think it's okay. So parent start. If we add a command, int command add, then we create a file executing process, and this file executing process has the flag internal set. The default value is false. This means we have a container process, and this container process is executing for every command. It is executing an internal version of it. And that's the reason why this flag is set to true at this point. So a new file executing process is created and the internal flag is set. Okay. This flag is checked at the start if this thing is an internal process, then it is creating the pipes. Mm-hmm. Mm-hmm. Okay. It is creating the pipes if it's internal, otherwise it's a container, and if the container does not contain any commands, then the command list is empty and nothing to do, positive. Otherwise, it is going through the file executing list and is starting all of the stuff. And if it is finished starting, then it sets the flag internal started. Yes, that's it. So this must be done. Okay. And then if we one moment. So if we are shutting down, then I think we need pipes close. Yes, pipes close. Boah. Then we need a different shutdown function. Theoretically. Internals free. Oh, this fall through is dangerous. we can in any case for shut down internals free. We have the iterator and we go through all the execution lists. Let's see. Command add. What are we doing at this? In this function v. Yes. Yes. This is the information of the internal process, and this process has everything we need on information. So we have in the internals we don't have anything in the list, so we can use this and we say delete. Yeah, that's it. We could use this variable to distinguish the shutdown process. If we need a distinction, we can use this. That's okay. But at the moment I'm fake. No. Whatever. Pipes create parent start. Parent start. Container start. Let's make it more clear. Internal start. Yes, container start. Internal start. Then pipes create. Shutdown. Internals. Shutdown container. If is internal. And here we have shutdown internals. And here we have return positive for the container. So let's see. If we shut down, we check if we are at a container or an internal. That's wrong. So that's it. Internals, otherwise container. Container internals free. Return positive. Internals pipes close. Positive. Okay. But we have to check, that's very important, if the internals have been started already, then we have to return positive. We are not allowed to delete the our children if we have started them already, then they have to be deleted by the abstract state machine. Okay. The file is getting bigger and bigger. It's compiling. Essentially, we have two different processes in one file. I don't know if this is cool. Okay. As soon as we have started our container, immediately after that we have to say guard log config is closed. At this point nothing should change, hopefully. Before that, at this point we can still change the configuration. But after this point we should not be able to change the configuration, hopefully. So let's execute this thing. What is happening? Could not execute file blah blah blah. Okay. Yes. We have used this operator. Oh no. Oh, come on. Operator, yes. Oh, that's so bad. Command add. We have to add the operators now again. Oh, the soup was too much. We have to use internal command. but a different version of it. No. No, I think we can. I think in this case it's allowed. It would be allowed too in this case. And in this case. Ooh, maybe we can optimize stuff. This thing is executing. This one, this version. And this one is executing this one. I think it's completely. It's too much. I think it's way too much. We can use this one. And we can use this one. Ooh, that was wrong. I am confused. So now I'm really confused. Okay, I think this is the one I can delete. I think it's okay. Command add, we can use internal versions for it. At least it's compiling, but we still have one problem. Forking using command, that's cool, but could not execute file. Okay, interesting, because it's telling us that it is, yes, it's executing the command, whatever. So let's see what is happening in function child execute. because it's telling us could not execute file, p argument 0. What is p argument? This is this one. P arguments. Arguments is... do we have arguments set anywhere? Arguments clear. Then we push back. We fill the arguments. The arguments should still be here. This function must be executed, and this is clear pushback. This command. Yes. That makes sense. We cannot save a pointer to a local file. Local. Yes, that's it. So this is running. Now a lot of stuff is working already. That's fancy. So that's very fancy. So full. I ate too much. Okay. So we are forking this command, and as you can see, we have a parent process, and the parent process is starting a file execution. And this file execution creates its own version in a different mode, in the internal mode, and the internal is forking. And going into the child supervise process. And we should not call this sub-exec, but internal supervise. It's not sub-exec, internal supervise. But it's quite cool already. The container is in the state internal supervise, and the internal is in the state child supervise, process supervise. The child is running. We can send a stop. Then this internal has seen the child is stopped, and it's running again. That's cool. That's so cool. So this is amazing. This is amazing. Okay. That's better. Uh, that's okay. We say signal continue. This list will be bigger in the future because we want to make a chain of commands. Okay. So it's a lot we have to do, but as soon as it's working, we have the paradise. Okay, so the arguments. Let's see. We do not want to wait at one moment. If we let's try to send. Should we say sync close? Should we call this function send close or sync close? Send and read. Yes, we should call this no, we should call this source close. Send close. Send source close. F divide is not send ready false. Source close, source close. What is happening if we send something? If the source is not enabled, return. If it's automatic, return. If we are not ready to send, return. If we are not internal, if this is a container, then and if not, no. If not internal, then return. List execution 0 send p data and len requested. Yes, that's okay. Okay, at which point can we send? Send ready. The internal, which is starting the first child, has to create the pipe, and then it is send ready. If send ready, then send ready is equal to true. So if the first is this cool, is this okay? Now we have checked the whole list, I think. This is getting out of hand. I don't know. So internal command add child execute. Send ready check. Send ready set. If send ready return. Okay. No, I don't care, honest. Do I care? I think I only need to check this. The container should, if we use the container to send something, the container should wait for the first process. If we write into the first process, then we write to this buffer. So this should be okay. Okay. So we are waiting. Send ready. We are awaiting send ready. And that's fine. So let's see. Oh, come on. Which is of pointer type. Is this true? Yes. Because that's a list of pointer. And again, unable to send data, not enabled. Oh, that's cool. Ooh. Read finished. Okay, that's cool. Unable to send data, not enabled. That is true because the default is it's disabled. We have to enable the source. It's not enabled. So this should be the first. This should be the first test. If we do not enable the source, here we are at internal supervise. We should in general, in the internal supervise, we should return children success. Okay. The container is checking for the children. If every child is finished, then positive, then it's returning positive. If one of them is negative, it's returning negative. And if at least one of them is pending, then it's returning pending. So this is fine. Here we can implement the timeout to do timeout. Parent start. Pipes create. We initialize the pipes. The default case is that this pipe is created and if we don't need it, then it is closed. This means it is created. The pipe is created completely. And then we fork. And then we start the parent. And in the parent we have to close read and write. We close the read part of the standard in pipe, and if come on. One moment. I didn't think that this will take so... Oh! Devil walks. Hello? How are you? What's up? Not a bit harmony. I'm fine. I'm quite fine. I'm kind of sleepy, but we are coding quite a complex process. But if we finish this process, then we have a very cool tool for C++. I want to execute Linux files in C++ in a cool way, like this. First person which I've seen using Vim. The first person, no, there are a lot of people using Vim. It's the one tool. It's very cool. So I don't know. Oh no! Stop! I don't know how. Do you know Linux? I guess. We are using the function fork. Do you know the function fork? Ah, yeah, you use Arch Linux. Cool. I've used Arch Linux at the beginning. It's quite cool. At the moment, I'm switching from Debian to Ubuntu. This computer has fork. If you have a program and you use fork, then this function is making a copy of your process. If one of the threads is executing this function, then you get it's called a child process, and the process is the complete copy of your process with all the open file handles, the data and the code. It's all the same. And usually you use this function if you want to execute another process. If you want to do that, then you have some options. The first option is to use the function system. It's quite a simple function. The system function. Maybe you know this function. But it has some drawbacks. The first drawback is that it is a blocking command. If you execute this function and you process that the file you want to execute takes a lot of time, then your parent process is blocked. You could create another thread, but you don't want to create the thread for every command. If you have 10 commands you want to execute in parallel, then you have a lot of threads you may not want to. It's not necessary. Not necessary in reality, I think. This is the first drawback, and the second one is you only get the return code. You don't get any standard input, output, standard error messages, and so that's bad. And you can't send signals through this process. Essentially, these are the the channels you can use to communicate to a Linux process. For example, the arguments, the environment, standard in, signals, standard out, standard error, the state changes, and the return code. And with this system command, you only have access to the arguments and the return code, I think. And that's all. So you're missing a lot of communication channels. It's a simple command. If you want to execute small stuff, then yes, the options are quite limited. And one very important and very dangerous thing is, if this string you provide to the system call is created, you should never give this command unprocessed user input, because this is a security issue. If you enter a command which is created with the help of a user input, then the user may use shell injection attacks, because this system call is executing the execution function, one function of the execution family, and this in this manner it's executing the shell. The cool thing is that you can use the pipe command in this string, because it's executing the shell, so you have a layer in between. It's well in the code, which would likely result in the world's easiest injection load. Yeah, yes, absolutely. So I want to avoid using this. So it can be useful. It can be useful, but I want something that is safer and much more powerful. And yes, and the next option is the next option we have is manual popen. The popen function is a little bit more powerful than the system call. Here you have I don't know if it's more powerful. It's different. With popen you can do something similar to system, but you have access to, you can choose between two things. That is, you can choose between standard input. If you this popen function is using a command as before, and it's again invoking the shell, so we have the same vulnerability. And with this type you can choose, you can open a process like a file, and you can read or write to this file. This means you can use this channel if you write to the process file, and you can use this channel if you read from this process file. But again, it's very limited. I want to have everything. I want to have complete control, and I can show you, for example, a lot of stuff is working already, so I can show you. And if you have Telnet, we can play on our game server. We have created a game server, and we can play Connect 4 if you want. But first I want to show you this thing. No problem. see, this is the process tree of a few of our test unit test program. This is our gaming server, and this is the process tree of our gaming server. So this is the main project in this stream. But we at the moment we are creating quite a complex and powerful process. Usually I'm only working in this project, but because this is quite complex, we have a unit test environment. And in this unit test environment, we have a parent process. I have to be careful with the name because I call a process something a specific class in C++. We have created a base class, and this base class can create a process. And in Linux, in the Linux system, if we start a process, then I call this an operating system process or OS process. So if I'm talking about processes, then I mean these things that are started in the C++ environment. And as you can see, we have this process tree, and the unit testing process, the parent process, is creating a file executing. And this thing is essentially creating an operating system process. And as you can see, the process is running, and now we can send a signal to this process like sig stop. And then we can see that we have complete control. We see that we can fetch signal, we can send signals to the process, and we can read signals like here. So we have these channels. At the end we have every channel, but at the moment we can read and send and read signals. So it's quite cool already. We can continue the OS process with signal continue, and then it's running again. And we can check and see and check this. At the end, we want to be able to concatenate commands like this because we want to have a convenient way to execute a bunch of commands. Like in the shell, like in Bash, I want to code. If I want to execute an external program, I want to be able to make it in a comfortable way, like in Bash. And at the end it's looking like this. So but we have to do quite a lot of stuff because we have to implement switches where we can decide in which direction we read and write and stuff, and then at the end we want to concatenate our commands. So we want to have a powerful process, but in this case it's quite complex. More or less complex. Okay, so we have a special environment here. It's not that easy. It's not that easy because I'm so greedy. I'm so greedy. I want to have everything. And I want to have internal in this file internally. It is a little bit complex, but I'm okay with that, because at the end it's making life very easy for me, because I want to be able to create the process. I want to create a file executing process. Our software structure in our projects is always the same. It's a recursive structure, which is at any point it's the same. We always have a function that is called process, and we always have a state machine, and we can always create other processes, child processes, by creating a process, configuring the process, and then starting the process. It's every time the same. We are creating an SSH server with it. We are creating a telnet server with it. We can create a TCP connection with it. Or everything is the same, always the same. Create, configure, start. And if the process, this file executing process, is finished, then we can start another operating system process, and we can communicate with this process through any channel, like if we are talking to a server. This thing is executed in parallel, and it's not stopping us, it's not blocking us in any way. We are just creating it, we are configuring it, and as soon as we have started the process, we can move forward. It's just started, it's in the background, and we can read and write like we want. So it will be quite cool, but unfortunately, because there are so many ways we can put these commands together, this makes the whole stuff a little bit complex. And also these functions are very old Linux functions, so we had to go through the manual and read what they are doing. The whole stuff, the big picture, the concept is to execute these functions. Basically, you want full control over your hardware. Well, that's really dumbed down, but oh well. Yes, but it's we are quite far. We are very far, because we have to do 4 steps. We have to do the core of this process are 4 steps. If you have if you understand the basic concept, then it's easy. For example, the first step is to create 3 pipes. A pipe is, you can use this function pipe2, and if it's just a pipe, and this pipe has 2 ends, an end where you can write and an end where you can read. So it's like a file where you can write and read. If you create a pipe, then in the kernel you have a buffer, and you have two file descriptors to this buffer. And with these pipes, you are able to communicate with your child, because as in the parent process, you create the pipes. You create, for example, one pipe. Then you have two file descriptors, and you can read and write, but it does not make any sense for you to read and write the same into one pipe. So this is used in a way like that. You create the pipe, then you have two file descriptors, and then you execute the fork function. If you execute the fork function, then you have a copy of your own process. And if you have a copy of your own process, then all of the open file descriptors are in the child process operating system process as well. Then you have the same file descriptors of your pipe in both your parent process and the child process. And the trick is, if you are in the parent, then you can close one end, because you don't, for example, in this example, the parent is writing to the child. And because it's writing to the child, it can close the one side of the pipe which is for the reading, and it can write to the other end. And the child, after the fork function, if the fork function is 0, then we know that we are in the child process, and the child is closing the right end, so it's not writing into the pipe, it's just reading. And in this way, these two processes can communicate with each other. So this is the basic concept. I don't know if I think today I'm bad at explaining, because usually I need a beer to have improved English skills, but today I think I'm quite confusing. I'm sorry. But because we have a standard input, a standard output, and a standard error, we need 3 pipes, and we have created these three pipes in the parent. And the first pipe we called standard input, and in the parent we have closed the read end. It's always a pair. A pipe is a pair of 2 file descriptors, and the standard input pipe is, all 3 pipes are copied to the child after the fork. So if we fork our operating system process, then we have a complete copy of it, and the file descriptors are pointing to a buffer in the kernel. And for the standard input pipe, in the parent we can close the read after the fork, because we don't need it, we just want to write into the standard input pipe. And the child is closing the right end of the pipe, and is just reading using the read file descriptor of the pipe. And this pipe is used to write data from the parent, writing into the kernel buffer, and the child is reading from the standard input pipe by using the read file descriptor of the pipe. And the standard output pipe and the standard error pipe is exchanged. Here in the parent we close the write file descriptor because we don't need it. We are using the read file descriptor, It's just the other way around, and the child is closing the read file descriptor of the pipe we have called standard out, and is using the write file descriptor. And the same for standard error. So we have standard input, standard output, standard error. We have the signals, and we can send arguments and environment, and of course the return code. So we have everything we need. This is running in the background, and we can communicate. The process in the operating system is doing something. We can check at every time the result. And because I want to have a convenient way of doing that, I want to be able to have a switch. I want to have a switch, and this switch should should tell the file executing process in the C++ environment from where we get the data for the standard input. For example, in the default case, I don't want to send anything to any process. I just want to have a closed input. Maybe I want to send data manually. Maybe I'm calculating some data and a signal and whatever, and I want to send the data every 10 milliseconds or something like that. Then I'm using the manual method, send like or write like writing to a file. And then I want to have the automatic approach, like creating the process and then say take the data from a string, something like that. And then I want to forget about the stuff. I just want to give a pointer and say, and take the data from there. So this is, and the same with the output. I want to say, I create a process, and then I want to say, all of the information you create, you can write to this string or something like that. So this is quite convenient then. And unfortunately, because we have two outputs in a process, we have two other switches, and it's similar in this case. So step by step, the last thing we wanted to do is, so the state machine is like this. We go to the start, then we check if we say the config is closed, everything is done, you can't change the structure after the process has started. Then we say start the internal version of a file executing process. So this is the core. And then we go into this state pipes create. We create the pipes with the pipe function. Here we get for each execution of this function, we get a pair of file descriptors for one pipe. The standard, we call this pipe the standard input, standard output, and standard error. And then we say, okay, now we have six file descriptors in our 6 new file descriptors created in our parent process. Then we say, okay, now we can fork. Then we are using the fork function to make a copy of our process. And this copy has the same 6 open file descriptors. And then we say, okay, if fork is smaller than 0, then there was an error. This can fail for some reason, then we have an error and we return. If it is bigger than 0, then we are in the parent. Then we are in the parent process. And we save this result of the fork function. If the result of the fork function is bigger than 0, then this is the ID, the process ID from the operating system of the child process. And as a parent, I'm saving the child process ID. And then I'm doing the parenting stuff. If the result of the fork function is 0, then we know we are at the child process. We are at the process copy. Then we are here. And then we can execute the child. And the child is closing some pipes and doing stuff. And then finally is executing some other process. In the parent, parent start. Here, yes, this is, here we took a break. In the parent, we are closing the read file descriptor of the standard input pipe. This is done here. But in the default case, we also want to close this thing because we want to tell the child that there is no data present. And if the buffer of the kernel is empty and this side of the pipe is closed and the child is executing the read function on this file descriptor, it's getting end of file, error end of file. The kernel is telling the read function, you will not get any data because there is no data in the buffer and the input is closed. So if we close this side immediately, then the child is not getting any data. And this should be the default case. And this will be done only if we don't need this connection. And this connection, we don't need this connection if oh yes, wait a moment, yes, if the source selector, of course, now we have to check the source selector, and if the source selector says if it's not enabled and the source selector is not automatic, then we have to close the write file descriptor of the standard input as well. So this is the manual. Should we call it manual? I think this is cool. Automatic, or come on, yes, step by step. Auto enabled. So okay, and auto enabled, manual enabled. Source enable, sync enable, send. Yes, that's it. So if it's not manual enabled and auto enabled, then we don't need it. And if we don't need it, then we can say close the stuff. Otherwise, we are using it. Then we need this connection and we keep it open. So this is cool. And in this case, yes. So this is the source, and in the pipe creation step, if we want, in the default case, we want to send all the data which is coming from the child process. For example, the child process is sending output through standard output. Then in the default case, we want to discard the data. And how can we do that? We can do that by opening def null, and use this as the write file descriptor of pipe standard output and standard error. This means we initialize the pipe. In any case, we need the standard input pipe in any case, but standard output may not be needed. The pipe may only be needed if the sync output manual enabled or sync output is auto enabled. Then we want to create the pipe because we want to communicate with the process. If it is not enabled, then we want to open a file, manual open, open def null for write flags can be create direct yes non-blocking non-blocking oder let's see common lib files is file non-blocking set yes. No, we don't need this. Non-blocking set, yes, maybe. Oh no. Oh, No, stop. I don't think we need the non-blocking. It's for the writing end. And the writing end should be blocking. So we need write. This must be the first one. Create, append, and append mode. Write only. The argument flags must include one of the following access modes. The flags, yes, write only. Write only. That's it. We want to have write only. Cool. And then we have to check the output. We have to check conforming to open is conforming to POSIX. That's cool. And there are a lot of errors. Return value on success. Return the new file descriptor. A non-negative integer. On error -1 is returned and error is set to indicate the error. Okay. If result is smaller than 0, then could not create write fd of std out. That's cool. And the same here. Oh, stop. The result is the file descriptor. This means the std out file descriptor for writing is the result. That's it. So, and the same here. If the sync out is manual enabled or sync error is auto enabled, then we need the data. And we have to create the pipe. Otherwise, we don't need the data. And we say result is open def null option write only. Come on. It's not beautiful, but whatever. Okay. That's not beautiful. We say bool needed. I want to make it a little bit this you can't read this. This is very bad. Needed is equal to this or that. Okay, so if needed, then we create the pipe. Otherwise, we create def null. If the result is smaller, nope. That's okay. One moment. And here we have So now we have to check if this is better. I don't know. We say pipe needed. If the pipe is needed, then we try to create the pipe. If this is not working, then return. Otherwise, on error -1 is returned and error is set to indicate the error. Usually I don't do this, but in this case, whatever, why not? Okay, pipe needed. So this should be fine. So next, pipe needed. If If pipe needed. Then we say create the error pipe, otherwise create this thing. That's okay. And then again create std error. Yeah, that's fine. And I think that's it, hopefully. So we create the standard input pipe in any case. We create the output pipe only if we need this pipe, if we need the data. And we need the data if we read it manually or if we read the data automatically. When it's needed, then we make the pipe. If we don't need it, then just initialize the write part, because we don't need the read part. Not reading anything, and the write part will be sent to the child process, and the child process should write to def null. If res is smaller than 0, then could not create pipe or write file descriptor because of this. Similar, if we have the error and we need it, then create error, otherwise create the write file descriptor for error. And so let's try to compile this thing. Okay. That's cool. That's very cool. So the routing and the concatenation makes this thing quite complex, but it is very useful later on. Okay. Okay. So now, in the testing process at the moment, we are not enabling anything, so we should have the standard case. We should not be able to send anything because it's not enabled, and we should not be able to read anything because it's not enabled. The process should execute and be terminated because there should be an end of file error in the testing program. Let's see. Okay, forking using command blah 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 could not set non-blocking mode, bad file descriptor. Parent start, file non-blocking set. Yes. Read. The parent start. Okay, the parent is closing the read part of standard input. It's closing the write part for standard input if it is not needed. We want to do this in the same way. So this is or, and if not pipe needed, then close. Stop flickering around. Come on. File non-blocking set. We can only set non-blocking, a file non-blocking if it is okay. That's a special non-blocking set of a file descriptor. Should we return true if the file descriptor is -1? File non-blocking set. If this thing is not initialized, then we should not execute this function. I don't want a silent error, I think. So we have to check if we needed the pipe and if the pipe has. Okay, let's see. Okay is true. If is bigger than 0, then ah. Okay, I think that's That's fine for me. If we have a file descriptor which is smaller than, theoretically we have to check this one. We have to check this one. And then we have to say true, otherwise we have to set the non-blocking. Okay. Okay, then we say true. And here we say the same. Okay, so now okay. Oh, nice. Oh, that's cool. Terminated. Oh, yes. That's so cool. Oh, come on. It's already 10 o'clock. So bad. Okay. The cool thing is it's working already. The child process, the child operating system process has terminated. No signal, return code is 0. It was successful and it was terminated. No bytes were sent and no bytes were read. Oh, that's not beautiful. Think. Okay, that's cool. So no bytes sent, no bytes read. Just terminated because it has nothing to read. Now we want to enable the sync. We can't send any data. Unable to send data, not enabled, and read finished. Why is the read finished? Because read finished because we got below 0 and we got below 0 because sync read, it was not enabled. Because it was not enabled, should we indicate an error? Yes, we should indicate an error. Unable to read data. So this would be unable to read data. Auto sourcing, not enabled. Auto, yes. Now we should get an error message, not enabled. Unable to send data, not enabled. Unable to read data, not enabled. Okay, now we want to read the data and we should get an output. I want to enable the sync. And I don't want to auto enable it. This means in the file executing process, in the testing process, I say that I add a command and I set the environment for the command and I want to sync enable. And which one? The default one, the standard output. If we enable the sync, then the default sync is the standard output. And then we enable the manual enabled flag. Okay. Sync read. Oh yes, that's no. No. Config closed. It can't be config closed. The index must be fine. This must be fine as well. Ah, yeah, yes. No. Oh. Because the read function first has to check if it's an internal thing. No. Send, or send. Okay, we are waiting for send ready. But for read, we say something else. If we are the container, if we are the container in the read function, read ready. Oh yes, oh, come on, sync read ft cell. Yes. But only if we have a command. If we have a command, p data was not declared. What? P buff, yes, okay. whatever. So in the read case, the internal must say, okay, read the sync of the last element. Ooh, the last element. Ooh, the last element. Is it a list? I think it's a list. No, it's a vector. Doesn't care. Always the wrong one. So I need the last one. I think that's back or something. Returns a reference to the last element. Undefined behavior. We should not call this to an empty container. This means we have to check if there is a size, and if there is a size, then we say dot back. The last one should be read. If we are not internal. If we are internal, then we check if we are enabled. Yes. Oh, 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 yeah. Unable to send data, not enabled. But the read function is returning something. Oh, that's so cool. And as we can see, we have read something already. We did not send anything because it was not enabled. We got an error, but we were able to read data from the child process. Oh, that's cool. A lot of work is to do, but we are moving forward to awesomeness. Okay. Now. Still, now I have this strange behavior, and I think there is this, a bug in the read function. We can fix this now. I don't know why this is buggy. Maybe because I'm doing strange stuff. So, buffer. Size of buffer. Size of buffer -1. Yes. And then mbuff len read is equal to 0. I don't know. Oh yeah, that's better. That's better. This was one bug. This was one bug. Environment. This is still a little bit strange. Why? Because, yes, I know. Okay. Yes, because this is not needed. Yeah. Okay, hopefully the output is fine. Yes, okay. Boah, that's cool. Oh, that's so cool. Holy shit, that's so cool. Because now I can say I want this command and I want to have this environment and I want to enable the default sync. Oh, that's cool. Now again, I want to enable the sync, but what if? Oh, that's not cool. That's not cool. That's not cool. Ho 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 ho. Wait a moment. The order of these commands is not right, I think. Because if I'm reading from the container and have not added a command yet, then we have a problem. Then this thing is... Yes, I have to do something, if not internal. If not size. I want to set the read ready flag. I want to set the read ready flag the same like the write ready flag. That's the shutdown function. Something like this. If not read ready and mlst execution.back. Do we have a front? Returns a reference to the first element in the vector. Okay, then we have to check this. P arguments dot front back read ready. So if I'm not send ready, but the first internal execution process is send ready, then I'm ready to send. If I'm not ready to send, and the last one is ready, if I'm not ready to read, and the last child process is ready to read, then I'm ready to read. Okay. So if I'm not ready to read, return 0. If I'm not internal, okay. I think that's it. As long as I'm not ready to read, I return 0. But if I'm ready to read, then I check higher priority is the container. If in the read case, yes, in the read case, send case, let's make it not ready. Yes, I want it to look similar. Ready, then the container, and then the enabled check, and then the mutex, then the file descriptor. Yes. Okay. So this is bad. This is bad. We don't need a write file descriptor anymore. So let's check. There is only one file descriptor, and that's this one. Yes. Send ready. This means, yes, no, yes. Mutex write should be at this point. Mtx read. We should not have a file write descriptor. Source close. Yes, that's it. This should be closed. Instead, send ready false. Yes, it's getting better and better. We don't have this one, and we don't have this one. Yes. Write failed. Okay, but that's perfect. FD read. Now the same here. Okay. And the last one, and the file, hopefully. Okay. Compile this thing. Okay. Now we can read, but we only read if we are ready. And we are ready if we set up the pipe. We are ready after setting up the pipe in the parent. We finalize the pipe in the parent. Okay. After finalizing the pipes in the parent, then we are send ready and read ready. Okay, fine. We only set the files to non-blocking in the parent and in the parent only if they have a value, if they have a valid file descriptor. Fine. If we don't need in any case these three file descriptors, we close the in file descriptor if it is not needed. Yes, okay. Something else. The read file descriptors for standard out can be not initialized because of this. Then we don't have a read file descriptor in this case, only the initialized version to -1. If this is the case, then we are ready, but it is not, yes, it's not enabled. So this is a double check in the read function we don't need. Theoretically, we are checking for is enabled. If not enabled, if not manual. Oh, that's wrong. That's wrong. We need something else. We need bool pipe needed. and the pipe is needed if we say not pipe needed but a sink used. Sink used if it's manually enabled or auto enabled. If not sink used, then unable to read data. Sink used? No. Manual enabled. Let's keep it simple. Not sink not used. No. It's okay. Ooh. Let's see again. If it is not enabled, then we go out. But if we enable the sync, then we have another check. Yes, we can say this is has a higher priority. If it's auto enabled, then it's auto sourcing. So but then if it's not anyways, so first we check if it's auto enabled. If it's auto sourcing, if the sync and source is auto sourcing, then this has a higher priority. Only if this is disabled, if the automatic sourcing is disabled, then or auto syncing, sync not enabled, source not enabled. And here we have to be careful. And fd read sync read fd read is come on is equal to fd read is no. The selector is just the selector itself, and for this after the selector we need a read file descriptor, and the read file descriptor is stdr read or stdr read, fd read. So fine. Now we have to remove this one, and this one because we want to, and this one. Yes, that's cool. Because we should we have to be able to read from the from this file descriptor or from this file descriptor. So this file descriptor is this read file descriptor or the standard error read file descriptor. Okay. We are coming closer and closer. It's cool. Now, now, very important. Okay. Okay. So we are very close. Two core things have to be implemented now. This is the auto sourcing and syncing, and the concatenation. So, one moment. Child terminated. Let's wait for the child to be terminated. This should be fine as well. Yes. Unable to send data. We can't send any data. It is terminated. Child terminated. Wait. Ah. Oh. Ooh. Yes, okay. Child terminated. Oh, that's an interesting function. Now, this function must be implemented. As size t index. Yes. If index is bigger or equal to 0 and index is smaller than the size of the vector, then return no, this has to work for. No, yes. Yes. this thing will only be executed by the parent process, and this is the reason why I can directly return if m is internal, then return this one. If I'm an internal process, then return the simple case. First the simple case, then if I'm in the container, then I check if the index is between 0 and the size of the list, then we have a pointer and otherwise I check all terminated is equal to true, and I say I have a file execution iterator, iter is equal to dot begin. I go from begin to end. If the process has not terminated, return false, otherwise return true. Okay, this means if I execute the function of an internal file execution process, then return that if the child operating system process is terminated. Otherwise, I'm in the container. If I'm selecting a specific process in the chain, I want to return the value of the specific process. Otherwise, I want to have the collective information if all of the child processes are terminated. And I can check this by running through all the internal processes and check if the child is terminated. If one of them is not terminated, then I return false, and if all of them are terminated, then I return true. So this is the container, this is the internal container, specific internal, and that's the container, all internals. That's cool. So this means, why did I have to press this thing a second time? This is strange. Okay. Hmm. Mm. Huh. Mm. Yes, that's bad. If comparison integer of different signedness. Yes, different signedness, that's fine. This will be the last function for today, I think. Code return, oh yes. This is a similar function. We could, let's see, a little bit later. The index, we have a problem here because we want to oh, that's bad. That's bad. If it's bigger than the size, then I get all of the internals. I don't want this. Ooh. Mm. Ah, that's better. That is better if that's better, I think. If the index is bigger than the size, then that's the wrong value. Then I have to return false. If the size is bigger than 0, if it's smaller than the size, then I can do something. I can check if I'm above equals greater or equal than 0, then I can return a specific child, otherwise I have to return all the childs. Ah, yes, that's good. Different signedness. Although it's still an error, we could say, should we make a cast? Is this fine? More or less. It's not a member. No match for operator. What? Is... I'm confused. Why I have this iterator? Semicolon. Yes, it's time to end the stream, I think. Const iterator. What? Why? Because this is a child terminated. Yeah. Yes, that makes sense. Const. I have to use a const iterator. Oh, that was working. Fine. Okay, then the last function. If I'm an internal, then I return this. If I want a specific container, a specific internal, then I return I can't return the return. I cannot return the return code of all the internals. This does not make any sense. So but usually I want to have the last internal, so I return the code of the last internal, that is mlst execution.back child terminated. No. Code return. Okay, so if the index is too big, then return -1. Cannot return. No return code. Index out of bounds. Okay. If not, and if the index is bigger to 0, then is positive, then I return code red. If not size. So this is the return code. So this is not cool because this can change. No, this can't change. This cannot change. Yeah, that's cool. Okay. And now return code. And now command set. Empty command list. Okay, but if it have a command in our list, then we can return the code return of the last one. Okay. Okay, this has been terminated. Yes, and that's the cool thing, because now we can check child terminated. Child terminated if we have yes, if we are out of bounds, then we shouldn't return false, because if the parent is making an error and asking for this for the bool of a non-existent child, then we should return false, because then the parent process gets stuck in the state. That's cool. Here we have a negative return code. Okay. What is happening in this case? Here the same. If we don't have if the index is greater or equal, if we don't have a size. If we don't have a size. Oh yes. So if we don't have a size, then the index, and the index is -1. If the index is -1, then we have to check again the size. Okay. Yes. Because otherwise we would get true, and we don't want. Should we get true if the child has terminated? No. No, I think not. Okay, let's keep it that way. The cool thing is, at the moment already, we execute the function child terminated with the default value of child terminated with -1. This means we are checking not a single element, but all elements, and because we only have one element in our list, we are returning true or false of this one specific element, but we should be able to do the same with the index, and that's true, that's working. So we can use the index, or we can just use the default value of give me the information of all processes. Okay, that's cool. That's very fine already. Okay, now we have to rate somebody. It's getting better and better. We are coding and coding and coding in this file, but the testing file is still very clean. We did not change anything. So, and this is the reason why we are doing it, because we want to have a clean parent of the file executing process. We want a convenient way to execute processes, operating system processes, or Linux files, and that's very cool. We can't send something because we have no source enabled. Is the send function usable already? Let's see. No, it's not usable because we did not if we are enabling the source, that is source enable, then theoretically we should be able to send something, but I think we will still get the error unable to send data. Hopefully. Yes. Unable to send data. But now we have a different ID, I think. No, the ID is the same, but nothing has changed because we are executing the send function. This thing tells us, okay, at some point we are ready because we waited for the ready bit, and the ready bit is checked for the first internal execution. So this is working, but as soon as we execute the send function, send ready is okay. We are at first we are in the container. The container is executing the send function of the first process because we always want to. The front and back is used because here I have the front and here I have the back. Every time I send something, I want to send this to the first internal file executing process, and every time I read something, I want to read from the last one. So in the read function, I always use the end of the chain, and in for the send function I use the beginning of the chain. Okay. But the beginning of the chain has tells me that the sand is ready because it has created the pipes, but it is not enabled. It is not enabled. Because I have to copy closed, config closed. I want to copy. I close the config so I cannot change the structure anymore. And then in the container, I check if I have a command in the command list. If I have something in the command list, then I want to say the first execution the first internal has a source in switch, a source selector, and this source selector should be the source selector of the container. And now it should it should work. Yeah, it's doing something else. Bytes sent. We were able to send stuff to the child, to the first child. The strange thing is that we were not able to it seems that we were not able to close the source because we closed the source of this function is the old version, so we have to again if m is internal, then if this was an internal thing, okay, it's doing something directly. If otherwise, if not list exec size, return, otherwise return source close front Now I see something very interesting, because in this specific case, because we have merged two different process modes with each other, we have in every function we see the two modes. The first mode is this one, and the second mode is this one. I don't know if this is a good idea, but okay. If it's internal, then log and close and send ready false. Yes. Send ready false, but then also at this point we are closing something. Disabling something. Yes. Okay. Oh yes. Super. Oh yes, everything is working as expected. Oh yes, we are very, very close. Now we are not waiting anymore for the child to be finished completely. So we see the arguments and the environment immediately, and then we see foo, and then we see ba. It's running, and then it is terminated. Oh yes, oh yes, yes. Okay, now I will drink a beer, because that's cool. Okay. Let's rate somebody. Oh, that's so cool. Who is still online? Frozen Flame. No, that's a game. Infotastisch. Suseseki. Ah, okay. eCache. Anonymous signature. Oh, let's see. Let's see what they are talking about. This is IT, I think. Let's see. What is Suseseki doing? She is making JavaScript. Let's rate Suseseki. I think she's cool. Suseseki. See you next time on Tuesday, and then we will implement the last selection stuff, the last routing stuff, and the chaining, and then we will make extended tests, and then we are finished with this very special complicated task, and then we continue with more chilled stuff. See you next time. It was nice to see you. See you next time.